Hey guys, can you get okay, so Tanish is outside right now, so he cannot speak. But anyway, let us start. Let me check the first paper. Okay, so the first paper is why has predicting downstream capabilities of frontier AI models with scale remained elusive? So that's from Hailey. So Hailey, are you here? Okay, Hailey isn't. Oh, Hailey's here. So Tanish, can you make Hailey a speaker? Oh, yes.
Cool. Wait, sorry, how does this usually work? Do the authors just talk about the papers, or?
Yeah, so typically all the each paper has like from 10 to 15 minutes. Yeah, and at the end maybe we discuss about the paper. So yeah, we can't really use any visualizations, unfortunately, but you can just sort of quickly go over the paper and maybe share us some insights. Yeah.
Yeah, for sure. So yeah, this is a paper that we collaborated with Stanford and Mila and University of Cambridge with, led by Rylan Schaefer. So basically, the core problem that we're trying to look at is predicting the evaluation scores on downstream tasks of language models before we've trained them. So like basically before, let's say we've got a model that's sort of GPT-4o small, before we train GPT-4o and spend a lot of compute trying to do that, we'd want, if we're the model trainer, we'd want to sort of guess what the performance is going to be and decide whether it's worth it, beyond just guessing the pre-training loss of the model via scaling laws. And so the problem is, even though some works have explored trying to predict these evaluation scores with scales and constructing scaling laws for them, it's a lot harder to predict those downstream accuracy scores and other metrics compared to just the pre-training loss. And so this paper, we're basically trying to look at why that is and how we can improve the predictability. And so specifically, because it's sort of an easier setting, we look at multiple choice evaluations like MMLU, where we're comparing across a small set of fixed options the log likelihood output by the model of producing each option. And so basically in this paper, what we find, our core claim, is that as we go from the pre-training loss produced by a model straight to the accuracy on a given benchmark sample, there's sort of a bunch of different transformations we have to apply when obtaining that metric, which all degrade the predictability of that evaluation metric. So like our figure 1 in the paper, if people have it open, basically shows this pretty well. If we start out with sort of the very smoothly scaling loss on a given benchmark sample, or the loss on that sort of target output from that benchmark sample, we can convert that loss into first just sort of the probability of producing that token or that string corresponding to the correct output. And because this is just sort of exponentiating the loss, it's very predictable to go from the loss to this probability of just producing the string under the model. But then there are a couple other steps before we get to accuracy, which are basically getting the probability of a couple arbitrarily chosen incorrect choices that the model assigns, and then comparing these probabilities to each other while also excluding the probability of outputting any other string, and picking the choice that the model assigns the most probability mass to. And so these thresholding and sort of masking out invalid completions effects reduce the predictability of guessing what a given benchmark sample's score is going to be ahead of time. And so like when we look at these aspects in aggregate, what this basically means is that if we're trying to correlate benchmark scores in aggregate or per sample with compute, as we use these downstream metrics, which are sort of closer to what we actually want, we care about whether the model gets the question right, not just how much probability it assigns to the correct answer. It's harder and harder to predict this actual like meaningful downstream metric compared to just the pre-training loss. And so it's like concrete takeaways from this are basically that if you do want to be training your model and have sort of some smoother scaling progress measure on, say, MMLU that you can use to track like how well you're doing before your model's MMLU score really takes off, we think that a promising option might just be to use sort of the loss assigns to the correct answer string, or the sort of probability within the vocab, not among the restricted set of choices when doing this. And so I think overall, like I think multiple choice with these log likelihoods is a pretty good setting for studying these benchmark behaviors, and multiple choice is a very valuable tool to have for sort of efficient LLM evals. But yeah, we hope to sort of extend this to further works like, say, human eval, where the model has to actually generate text. That might be more meaningful.
That makes a lot of sense. Thank you so much. Oh, by the way, did you you also have another paper to present later? Is this paper very closely related to your another paper?
Oh yeah, sure. Yeah, I could talk about that paper now or later.
Oh yeah. What shall we do?
Yeah, I can just briefly mention it now. I guess the other paper is a paper sort of on evaluation more broadly for language models called Lessons from the Trenches on Reproducible Evaluation of Language Models. So it's a paper that we wrote that sort of chronicles a lot of the things we've run into and problems that we've faced when working with evaluation while maintaining and building the LM evaluation harness, including collaborations with the Big Science Workshop using the harness there, and other sorts of extensions. And so in that paper, we sort of go over a bunch of the challenges that one can face in evaluation of language models, and like some of our suggested best practices for mitigating the impact of those challenges. There aren't really any like perfect fixes here, but there are many like options one can take, like basically just improving reporting standards around evaluation. Yeah, and I guess another thing that sort of ties these two papers together is that in the appendix of the Lessons from the Trenches paper, I'd highly recommend people check out Appendix A, which sort of lays out some of these details of how multiple choice log likelihood based accuracies are computed for large language models, and other details about like perplexity and normalizing metrics for tokenization. Some of these details are sort of things that have been implicitly used in the GPT-3 paper, other major LM papers that introduce new models and also do their own evaluations, and are used in the harness, but these sorts of details don't really make it into papers or aren't talked about too much online. So it's helpful to have this information chronicled in one place.
Thanks for your presentation. So I see a few like people in like Technium. Do you want to join as a speaker? Okay, never mind. Sounds great. Tanish, do you think? Okay, give me.
Yeah, hello. I'm still outside a bit, but I had a quick question for Hailey. One question I had was like with some of these models, they like the ordering of the multiple choice questions affect the performance of the models. Have you looked at like the scaling laws of that, and if that's something that like just different ways of like how the questions are modified affects the performance? Any analysis of that?
Oh, yeah, that's a good question. So we haven't yet explored with, say, varying the prompts and varying like answer choice order and seeing how the predictability is affected. We very much would like to. I guess like some of the evaluations that we use in the elusive paper are not prompted in the MMLU style. So like the ARC challenge, for example, results that we show, that's implemented in a style where basically you just give the model like Q colon the question and then A colon, and then we score the log likelihood of the model outputting sort of like the string corresponding to the answer choice. So it doesn't actually know what the four answer choices it has available are. So in that way, like there's no real like recency bias or bias towards predicting answer A, and we still see these effects.
Thank you so much. Shall we move on to the next paper then? Okay, great. Thank you, Hailey. Now, our next paper is an image is worth 32 tokens for reconstruction and generation. So I guess this is my turn to speak. So this is actually a very simple short paper. So in summary, this was released by ByteDance. They released this. They presented this new tokenizer named TikTok because, well, they are ByteDance, so it's named like TikTok. So TikTok is a compact one-dimensional tokenizer which can present 256 times 256 pixels image with as few as 32 discrete tokens, meaning 8 times fewer than the commonly used two-dimensional tokenizers. This leads to a substantial speedup on the sampling process, like 410 times faster than diffusion transformer XL2, while obtaining a competitive generation quality. So the reason why this speed up is possible is obviously because you are dealing with 8 times fewer tokens. Other fraction, I don't know much about it. Probably, it may also have to do with the fact that the now latent variables are super compact, so it may be much easier to model the distributions. So this method is very, very simple. So TikTok first patchifies 256 times 256 input image into a 16 times 16 times D patches. Let's call it P. So D is the hidden dimension. And this patches are flattened into 256 vectors of each of dimension D. Then then we concatenate this P with K latent tokens. So it's going to be like you have 256 plus K vectors of dimension D. And now we apply a vision transformer on this and take the output of K vectors of dimension D. So and now your output is just K vectors of dimension D. And then it is fed to the typical vector quantizer used in VKVAE and so on. So now you have K tokens, each of which is discrete. And once Tick token is trained, like with this architecture using the standard reconstruction discrete autoencoder loss, they trained mask gate using the TikTok as its tokenizer and compared against the baselines. And now they achieved substantial speed up, good performance. So a few observations. So scaling up tokenizer, so their model size, plus using one-dimensional representation enables more compact latent size. So, and intriguingly, we find that with they found that with only 32 latent tokens, that their largest TikTok model achieves performance better than two-dimensional VQ-GAN model using 256 tokens. So this observation suggests that as few as 32 tokens may be sufficient as an effective image latent representation, which optimizes the utilization of image redundancy. So this is a big progress, I think, especially, this obviously applies to, firstly, this obviously applies to like a context compression. So for example, if you are dealing with many images, and if you want to feed many pages of documents into models like GPT-4o and want to interact with it, then the context gets very, very long because each image takes up like many tokens. Like typically, like if it's high resolution, typically it takes up like 700 tokens each, which is very long. But this way you can reduce the token count substantially. So this is huge. And obviously this can be applied to videos as well. Videos, it takes up even more tokens because there are so many frames. So I'm very looking forward to when they apply this to videos. So yeah, do you guys have any question?
Yeah, if people have questions, they can reply to the space. So feel free to reply to the space and ask questions about the papers.
Tanish, do you want to ask anyone, like William, be a speaker or not?
Depends. I don't know if anyone wants to be a speaker, but if they want, they can request, I guess.
Oh, okay, yeah, sure. So yeah, this paper is very simple. So I don't think there's much more to discuss. Well, simplicity is probably a big point of this paper. It seems like very easy to reproduce. So yeah.
Cool. Maybe. Yeah.
Are you inside now?
No, I'm still outside, but it's a little bit less noisy, so it's fine, I think.
Okay, so
I can cover the next one. So the next paper is Autoregressive Model Beats Diffusion Llama for Scalable Image Generation. It kind of connects nicely to the previous paper that Aran just presented. Basically, it's trying to apply Llama to image generation. The approach it's taking is it's an autoregressive model. There have been a few papers that try to apply Llama-like approaches to diffusion, and taking like the latest architecture, like the architectural changes of Llama and applying it to the DIT, the diffusion transformer. In fact, like our paper HDIT, the hourglass diffusion transformer, we used a lot of changes from Llama and applied it there as well. But this is different because the DIT is like for diffusion models. Here we're trying to do like an autoregressive model, so it's just like a standard transformer. And yeah, so basically for that we need to be able to tokenize the images, and then we can just do an autoregressive model on that. So they have a trained tokenizer here, and they have I guess a very high quality tokenizer. It's got a good reconstruction quality. It's as good. It's basically like a VQ-GAN, but they're saying it's as good as like some of the continuous autoencoder or continuous reconstruction. So like if you look at like stable diffusion, the stable diffusion VAEs, it's like as good as those in terms of this quality. So they're saying, yeah, like this is a very high quality tokenizer that they've trained. And so because it's competitive with those sorts of other approaches, they think that helps then with the generation and training I guess a Llama model for generating with those tokens for that tokenizer. So yeah, they have they have trained various sizes. I think it was like 300 million parameters up to 11 billion parameters that they have their Llama model that they trained on, these image tokens. And so they trained on, for example, ImageNet 256 by 256 and got an FID of 2.18. And, that's like outperforming some of the LDM or like the latent diffusion models and some of the other models. And then on top of that, they can also apply standard transformer optimizations. So for example, they tried the LLM and they were observing like 326% to 414% speed up compared to the baseline settings. So yeah, basically it's like you can make it also faster with a lot of the already existing tooling of language models. So the nice thing is like, yeah, basically you take this language model, one of the existing tooling and engineering, and you can apply it directly to image generation. So it's just a very simple paper, I think, in terms of like engineering and it's just kind of I don't know. I didn't find anything like any sort of special methods or anything. I think it's just a very well-engineered model, and I think they talk about it as being a very good baseline. So yeah, I think it's just an interesting paper. And I think, for example, if they used to sort of like tokenize this from the previous paper that we just talked about, maybe they might even get better results. So maybe the two papers could be combined in some way. But yeah, I think that's kind of the summary. Sorry, I think it's still maybe a little bit noisy here, but hopefully you guys caught all of that.
Yeah, no problem. Thank you. So I do have a few questions or like concerns with this kind of autoregressive approach to generate images. So, in the case of non-autoregressive approaches like diffusion, like the paper you released, hierarchical diffusion transformer, those, they use hourglass architecture. Basically, you can compress the image into like a smaller time steps in the middle of the layers. I think that's a very huge advantage to sort of make the model very cheap. But if you are doing autoregressive generation, you cannot really use hourglass architecture because you are sort of violating the causality, And so I was thinking like if we sort of could reduce the number of discrete latents substantially, like the previous paper, maybe we can sort of consider, even with autoregressive model, we only sort of generating in like the compressed latent space, so it's probably okay. What do you think? Do you think we can still do like a hourglass architecture on top of the compressed discrete latents?
Yeah, I mean, I think you can apply hourglass here too if you really wanted to, because like hourglass was the hourglass architecture was originally developed for text generation, and so it was applied. If you look at the hourglass transformer paper, it was like the hierarchical transformers. Hierarchical transformers are more efficient language models. I think that's the paper. So it's certainly possible to apply it here as well. I would say, but of course it's. The other thing is though, like, it's more so of like you have all the existing sort of tooling and engineering around optimizing the performance of transformers for autoregressive and next token prediction. So it's also like you're able to apply all those advances here as well. So it's also like, yeah, maybe speed maybe not as much of a concern if you're doing it with like an already like the sort of Llama like architecture where there's so many optimizations for making it fast. But yeah, it's certainly a good point that you make, and it's certainly worth considering.
Thanks for addressing my concern. Okay, Tanish, do we want to move on to the next paper?
Yeah, or if there were any other questions for this paper, that's fine too. If anyone wants to reply and send any questions. Okay, if not, we can move to the next paper.
Yeah, so the next paper is mixture of agents. And Ben, he's here. He can he's one of the co-authors of this paper, so he can speak about this paper. Or if there's any of his co-authors, they can do too. So
yeah, I've invited him to speak.
Hey, yeah, so I'm Junlin, so I'm the author of Mixture of Agents. I'll be introducing a mixture of agent, which is a novel approach to harness the collective strengths of multiple large language models to increase model capabilities. So our MLA architecture adopts a layered architecture where each layer would comprise of several large language model agents. And for each layer, those agents will take the outputs from the previous layer as auxiliary information to generate a more refined response. So this approach allows MOA to kind of effectively integrate diverse capabilities and insights from various models, resulting in a more robust combined model. So yeah, we define those large language model agents into two distinct roles: the proposers and the aggregators. So the proposers would generate the initial reference responses, and the would synthesize different responses from different proposers into a single high-quality response. And MLA is a iterative refinement process. So we, of course, did studies on whether like this increased number of layers help with actually the model capability or final model performance. And I think from our study, we found that MOA benefits from that, and it does increase with the number of layers, the performance. And also, we also found that having more proposers and more diverse proposers also helps with our final model capability or performance. And yeah, so so we did evaluations on common use language models to judge benchmarks such as Alpaca Eval 2.0 and MT-Bench. We did achieve state-of-the-art performance on both of them with just open source mixture of models. Yeah.
Thanks for presenting. This is a very interesting paper, in my opinion. So for example, you also achieved huge performance boost on math benchmark. And generally speaking, how much more inference compute are you spending with like a 3-layer versions compared with the baseline?
So there, I think figure 5 in our paper, we did show how much in terms of cost our MOA architecture does. So I think 3-layer is definitely a more costly approach. It's about like it's a little bit more than twice the cost of using just 2 layers, and using 2 layers is like more than like 2 times or 3 times the cost than using a single model. So, but we did plot it like a Pareto front cost curve, and we show that in terms of budget performance per budget, where our MOA is able to stay on that Pareto front.
Yeah, that makes sense.
Sorry, maybe I didn't catch this, but like with the proposer models, like these are like different like types of language models, like different pre-trained language models. Is that correct?
Yes, they are. They are different language models, but they can also be the same language models. In which case, we're doing a parallel sampling if they're the same language model.
Okay. Or have you tried like the same language model, maybe with different prompts or things like that, for example?
Yeah, we still try that, but that's something, we kind of had in mind when we were trying things.
Okay.
We just use temperature for.
I see. Okay. So what are the language models that you've tried, like different language models that you've tried, I guess, as proposer networks?
Yeah. Oh, so the language models we use are the Quinn families and Mixture 8x22b, Wizard 8x22b, and the Llama 370b, and also the DBRX. So those are 6 open source model in our reference architecture.
Okay, yeah, that's cool.
Thanks.
Does anyone else have any questions?
Have you tried? Are you trying any other benchmarks besides the ones on the paper? Because it'll be very interesting. Like the fact that it got such huge performance boost on math would mean that you can also expect.
Yeah. So we also try on Flask, which we beat GPT-4 in terms of correctness, factuality, insightfulness, and completeness. We also, not in the paper, but we also try reasoning tasks on our own after we submit the paper. So we tried it on math, human eval, and CSQA. So we were able to beat the baselines or the proposal baselines with MOA, but we couldn't really beat GPT-4 on reasoning tasks. But at least it's not doing worse, and we're able to beat like the baseline models, which is Quinn 110b.
I think it's totally okay not to beat GPT-4, but so you still got like a significant boost, right? So yeah, I think that's great. So yeah, if you like if you try more benchmarks and release some results on Twitter, yeah, we will be very much looking forward to it.
Yeah, thank you. Yeah, we will let you know if we have more results on that. Yeah.
Yeah. Sorry, there's some echo in the room here. So yeah, we will let you guys know. And also, this is kind of the most primitive and most simple way of kind of multiple agents collaborating. We in the future we're iterating on a kind of a more sophisticated approach, and also optimizing on the latency and cost a lot more. We have kind of a streaming inference approach that we're iterating that seems to work quite well. So definitely we'll keep the community up to date.
Thank you so much.
Cool, thanks. Yeah, thanks for sharing. It's really interesting. Thank you.
Sorry, any questions you guys have? I couldn't hear, so.
I was just saying thank you. I don't know if there were any questions. I think, yeah, we haven't seen any yet, but yeah, it was a really interesting presentation.
Thank you.
Aran, I guess you want to move on to the next paper?
Yeah, so the next paper is Improve Mathematical Reasoning in Language Models by Automated Process Supervision. So this one's from Google, released yesterday. Let me see. So yeah, okay, in summary, they used MCTS for the efficient collection of 1.5 million high-quality process supervision data. So process supervision means that I can explain later. So and this method is called Omega PLM, and achieve improved the performance on math benchmark from 51% to 69.4%, which is a significant boost. The entire process operates without any human intervention, which makes this method financially and computationally very cost-effective compared to existing methods. Existing method actually does have to, well, actually there are some unsupervised methods as well, but if you process reward model typically requires human annotators to look into like a correctness of each step of the solution, which is very expensive. And OpenAI did that on like 800K steps of math benchmark solutions, which is obviously very expensive. So as a background, PLM or process reward model is a reward model but trains the reward at the end of each step. Typically, each step corresponds to a unit, like a reasoning step or a sentence. But in this paper, the unit is seems to be like a consecutive n tokens, which apparently works fine. I could be wrong, but this it is a bit unclear, but this seems like it. So the result is that their method outperforms human annotated large dataset PLM 800K. So essentially outperforms the human annotated dataset, which is very impressive. So this is probably thanks to the greater number of data points and the fact that PLM 800K is using the data from GPT-4, which has slightly different data distribution than the model they used. I think it was Gemini. It doesn't seem to be using. So the thing is that, yeah, this is probably not the Gemini 1.5 math focused one released recently. So looks like not the math version. And also they achieved accuracy of predicting the so they also they are trying to process a reward model. The accuracy is 70%. This means that the model can accurately tell whether the next step is the generated current step is correct or not with 70% accuracy. So this doesn't seem too bad, but obviously far from 100% and more than 90%. I think humans can do much better. Yeah. But obviously, this is just a synthetic data. So I think beyond that, we need to have actual human labels. So I think this is a good for initialization, and then we can boost the performance by human, I think. And beyond this, it's probably difficult to just do unsupervised pure approach. So as for the methods, the label for process reward model was given by Monte Carlo estimation of the state, which is synthetically produced by MCTS. This algorithm swiftly identifies the first error in the chain of thought with binary search and balances the positive and negative examples, and which ensures both efficiency and quality. And they also used what is called weighted self-consistency algorithm, but I didn't find any details about it. It seems like one of the key components. I presume it looks something like this. So after generating many trajectories with different final answers, the answer whose sum of Monte Carlo estimation of state achieves the largest value. No, probably it's more like a process reward model, like a confidence probability that's probably used. It is chosen as the final answer. So yeah, it's just a more fancy version of self-consistency. There are a few limitations. So firstly, this approach still requires some human supervision in the sense that they're using the pairs of questions and final answers. So yeah, So in particular, this means that it is limited by the number of questions, existing questions, which is not a huge constraint. But obviously, you cannot do something like alpha geometry, which demands, which sort of needs that there are infinitely generatable like questions. And for problems where pairs are less scarce, this approach may be less effective. And in particular, this approach needs to be modified if a task of interest requires each step to be correct, rather than only the final answer being correct. So for example, if the question is about proof, it requires each step being logically sound, and there's no final answer to use. So in this sense, the proposed approach cannot be naively applied to general problems. Obviously, I think it can be applied, but as you can tell from the fact that PLM accuracy is only 70%, I think some steps has weird intermediate steps. So yeah, general problems do not have the format of like final answer, and like typically each step accuracy means a lot. So yeah, this limitation still exists, and this is also true for many other synthetic approaches like this one. So sorry, I forgot to tell you, but this approach also outperforms the existing synthetic approaches like Shepherd, but not with a wide margin. Okay, so actually there was a very related work yesterday as well. The title was something like Accessing GPT-4 Level Math Olympia Solutions via MCT Monte Carlo tree self-refined with Llama 3 AB. So this one, actually they used Llama 3 AB. And this is another MCTS work that significantly improves the math capability of LLM. So they improved math performance from 24% to 58% using Llama 3 AB. And this performs on par with GPT-4 Turbo on Math Odyssey benchmark. I don't know much about this Math Odyssey benchmark, but I think it looks like this is somewhat a bit harder than Math benchmark, I think. So they used reflection and refinement of generated answer and generates reward by itself. So they didn't use PLM-based approach, but they still used MCTS. Yeah, so this is a very significant performance boost. And the fact that even Llama 3 AB can perform on par with GPT-4 Turbo is very impressive. So yeah, that's about it. Do you guys have any question?
If there are no questions, oh yeah, again, people can reply with questions. If there are no questions, we can move on to the next paper. I don't know, depends.
Oh, yeah. We have Yam today. If he
Oh yeah. Yeah, if he wants to join as a speaker, he can join. I'll invite him over. But if not, we will move on to the next paper. Let me pull that up. So just again, I forgot to mention this before, but the paper list, I did share it. You know, the papers have been going through. Aran posted it on Twitter. And then what else? So yeah, the next paper is a large language model for therapeutics, which is a paper from Google. So let me just quickly pin that to the space. Give me one. Wait, Aran, I guess you didn't tweet that paper. Let me see. I'm looking for it.
Oh, let me find it.
Okay, I found it. So for this, I pinned it to the space now. So, or it should come up in a moment. So this paper is released by Google. Yeah, for this paper, they've trained, it's a language model that's from from PaLM 2. So they have PaLM 2, and they're fine-tuning PaLM 2 on a bunch of drug discovery data sets. So that's like, they have like 709 drug discovery data sets comprising of 66 tasks formatted for instruction tuning. And so it comes from this repository called Therapeutic Data Commons. And it's got a whole bunch of tasks regarding drug discovery. So things like, for example, if a drug if like you give some drug, if it crosses the blood-brain barrier, or the success of this drug, or like the toxicity of the drug, all these sorts of questions you can ask about for example, some chemical that you give it, amino acids, things like this. So they fine-tuned PaLM 2 on this data set, and they were achieving near state-of-the-art or exceeding state-of-the-art on 43 out of the 66 tasks. And it's very good at, like, for example, combining the text representation of the drugs, which is called smiles, is the text representation is smiles, and also it's combine that with just like text questions and things like this. So it's very good at doing that. But like if you have questions that are solely about the drug itself, the small molecule drugs, it kind of maybe underperforms. It's good at, like, I guess, like if you have like different sorts of, if you ask questions about different molecules and amino acids and different things together, it's quite good. But like, for example, with the actual drug string, because like basically they're representing the drug, like the small molecules, as a string, and that's not always going to be the best, because like the molecules have like some sort of physical representation. Like, for example, we could represent them as graphs or other sort of approaches, and those approaches are usually more effective here. So that's one limitation that they have with this method, because they are just using a language model, so that can be a little bit limiting. But they also are observing some interesting results just overall with positive transfer. So like training on, you train a model on just like questions about just small molecules versus training it also on questions about like proteins and nucleic acids, and like it's actually improves performance if you train on all of it than just training on small molecules, which means there's like some sort of positive transfer going on, which is interesting. So that's kind of interesting to look at, like the positive transfer between, I wouldn't say modalities. I mean, it's like different types of molecules. You have like small molecules versus proteins and nucleic acids, and asking questions about the small molecules versus asking questions about proteins, and like training on both of them improves performance on the small molecules as opposed to just training on the small molecules. So there's some interesting positive transfer things that are going on as well, that I think it's worth, like, that's something interesting to study further, I think. But yeah, I mean, it's just kind of I think more of a preliminary paper showing, like, again, fine-tuning these models on this sort of therapeutic therapeutic task data set, this sort of drug discovery data set, and it's getting models that are able to perform well on that. But again, I think being a language model can be very limiting in this sort of case, because it's you're representing these molecules and proteins and nucleic acids as just strings of text. So I think having some sort of different representation for that may be useful. And that's something that could be explored further, different ways of representing it and passing it into the language model. But yeah, I think overall it's a very interesting kind of study. And I'll probably likely do a deeper dive in this paper and write a thread about it and kind of more in depth. So this is just kind of a quick kind of overview. But yeah, I think this is a quite interesting paper overall. And yeah, so just been really interested, like the kind of work that Google has been doing in the health space. So yeah. Are there any questions about it? Sorry, again, it's a little bit noisy here. Hopefully you heard all of that.
What I think is really cool about this paper is the prompt structure, if you've seen it. Basically, the way they build the prompts is something along the line of sampling random molecules and then going on and bringing the context for them, like fetching a context, literature review, and so on. And then the prompt goes something like, please answer the following question in the topic of drug discovery, and then they put the context, and then beyond, after the context, they have a series of different instructions that are completely different and are on different topics and subjects. And it is really cool to see that with this simple prompt structure, they could just embed, just because the way the prompt is built, so much information about the different interactions between the drugs and how and the different tasks that you need to do. It's not just an instruction type data set like we do with fine tuning and so on. It's a little bit more than that, because they kind of take properties that you can say that are tabular in nature and convert them to a textual form as if they were instructions. And I think it gives a lot of ideas. If you read the paper, it gives you a lot of ideas of how do you create prompts that are interesting for instruction tuning and so on, if you don't have the actual textual form of those instructions. If you just have, let's say, data of tabular data, and you want to train an instruction model that somehow knows this data. Anyway, that's just something I wanted to point out because it's interesting in the paper, and I think anything else we all agree. We all understand at this point that if you have a powerful model, it will work pretty well on a string of text, and if these text represent molecules and the model is powerful enough, I think we all understand at this point that it's going to be a good model. But this is a little bit more than just crunching more and more and more flops. So yeah, just wanted to point out.
Yeah, I agree. But I think in some sense, I still think, at least for some of these tasks, this sort of text-only approach, or at least using this kind of just the standard POM2 model or something, it may not be ideal. For example, like one of the tasks, like predicting binding affinity. So you have to predict like the binding constant. So like that's like a kind of a numerical value you have to predict. It's like there are a few tasks like that. You're predicting numerical values of like, and these are values that you want to be, pretty accurate for. And like, I don't know, to me, it seems like, we know how language models often struggle with some of these numerical tasks. I feel like, directly doing, having to predict for that might be a little bit, it might be a little bit difficult, and this is maybe not the best approach for that per se. I don't know, I don't know if you have different thoughts on that, but at least I think, that's the kind of what I've been thinking. But then there are other tasks like, some tasks are like kind of yes/no questions, or like, for example, selecting different options of like amino acids or peptides and things like this. And like maybe that, like those are, like, I think there were some questions about like, okay, predicting, like for example, does it cross the blood-brain barrier or does it not? So that's a yes/no. There's some other questions that are easier like that, I think, that, and are better suited for language models, I would say. So that's what I was kind of curious.
If we're going this route, we can ask, why would we use a textual language model in the first place? We can use a specialized model that is built for that. But, we are in 2024, and language models are really cool, and people are bending their problems to be in a textual form, so they can just fit a huge language model or anything. And yeah, look, it works. I agree, but I think it has value at the end. But yeah, you're totally correct. If you build a model that is specific for this, probably you can do something that is more, you can say, specific or tuned for this or efficient. But we are where we are. So
yeah.
Cool.
I guess, what is the next paper?
The next.
Or does anyone have any questions? Does anyone have any questions before we move on to the next papers? Okay, the next paper I think was supposed to be, we were supposed to have someone else speak, but I think they're not here, or they're unavailable right now. And then we were supposed to also have Hailey talk about the LME harness paper, but she's no longer here in space. I don't know what happened.
I guess she talked about it a bit, so I guess she sort of finished it.
Yeah, I guess. Okay, in that case, we will. She's not. If she comes back, she can talk about it more. Otherwise, I will talk about again the next paper, another paper, which is towards a personal health large language model. And let me pin that also to the space. Give me 1 second. Okay, so this is another paper from Google, and this one is basically training a model for personal health applications. So basically, they fine-tuned Gemini on a bunch of like personal health data. So for example, things like time series sensor data from wearables like Fitbits or Pixel Watch. So you're measuring things like the heart rate and, you have all the sort of like, this sort of personal health data that you're measuring, like sleep, for example, your sleep, how the Fitbit will provide the sleep information or your steps and things like this. So you have that data. You also have so there's a variety of tasks that they look at, for example. So they look at tasks like where you get that data and then you are asking, for example, a sleep medicine expert to provide maybe recommendations based on the data and based on what the patient is reporting, and then you predict. You predict, for example, what those recommendations are. So that's one task. You can do another thing where it's like, for example, predicting what the patient would report based on the time series data. So for example, based on this variable data with the user report having difficulty falling asleep. So for example, that's another task. So it's a whole bunch of like tasks regarding, the personal health. Mostly it seems to be focused on sleep. Like that's one of the main ones. I guess when you have the sleep data and then they also get these sorts of like case studies from, sleep experts. So they actually have a bunch of sleep experts. They have six sleep experts that they had them interpret a variable data and then provide a kind of ground truth, like this is the interpretation of it, and like what are the insights and what are like some problem, what maybe some recommendations, things like this. So they have those sorts of insights. They also have like fitness experts as well. So they also had like fitness case studies as well. So they had these different case studies, and so then they trained a language model. They trained one. They had this data set of the case studies for like sleep and fitness, based on what the experts gave them, and then they fine tuned Gemini. On that, they use Gemini Ultra 1.0, so they fine tuned that model on the case study. And basically they were showing that like they're getting approaching expert performance on these case studies as also evaluated by the experts. And then they also had another task where you're predicting like the patient outcomes from the variable data. Like I mentioned, maybe from the variable data you can tell if the patient is going to say that they had bad sleep or things like this. So you can try to predict that. And so like this is very interesting because it's time series data, and so they have like an approach for doing time series data where they kind of like basically try to inject the time series kind of data kind of directly into the language model, kind of like it's represented as tokens. I guess it's like you have the data is kind of in the token embeddings. They refer to another paper called Helm. I haven't looked too much into that paper, but I guess they have this specific approach for kind of injecting the time series data into providing that to the language model. So it's not just like you're providing it as text. There is some another approaches of doing that. So they had this approach, and basically they fine tune the Gemini model on that to predict the patient reported outcomes. And I mean, again, they are also getting good results with that. So I mean, they had a pretty large data set of like 4,759 individuals. I guess it comes from some other data set called the Google Digital Wellbeing Study, where they got that. That's where they get the data from. And yeah, I mean, yeah, I think like, you know, it's better than just doing, I guess, yeah, it's better. It's basically as good as like specialized models, I guess they were showing like on it. They did like for this specific task of predicting the patient outcomes. And, you know, they're looking at like area under the curve, for example, and they're saying like it's pretty much as good as the like a logistic regression model that they have. Like that's their specialized model. And yeah, then they, you know, did a qualitative analysis. And yeah, but yeah, I think it's again another interesting study of how, you know, these models can be used for personal health applications. I think that's been kind of an area that's been a little bit underexplored so far, and so it's good to see these sorts of papers come out where you can take, you know, this is whole, you know, a lot of this discussion about like digital health and, you know, the insights you can derive from digital health, and now we're trying to use LLMs to basically help derive these sorts of insights. I think that's a very interesting direction of research. So yeah, I think you know, it's kind of different from some of these other models that are, I think, more designed for doctors to use, and or maybe for researchers to use in the biomedical space. And this one seems like something where, like, you know, a consumer could use this sort of model and get relevant, you know, personalized feedback. So I think this is, again, a very interesting direction, but of course, still very preliminary. But yeah, I think that's all I have to say about this one. Again, I probably might do a deeper dive in this on this paper as well. Probably, we'll see. But yeah.
There is something interesting to note about this paper is that they trained on multiple targets at the same time, and we've already seen this on a very notable fine-tuned OpenLLM that we know today, OpenChat, where in OpenChat they had two different data sets. That one came from GPT 3.5 and one came from GPT 4, and they basically prompt the model before each of the instruction, like GPT 4 correct or GPT 3.5 correct. And obviously, in real life, you prompt the model GPT 4 and the model to just prompt to encourage the model to give you a better result, you can say. Overall, at the end, this approach yielded an extremely powerful model at the end. So what we see here on this paper is something that is on the same line of ideas, you can say, where they had just classification data and numeric data and things that are, you can say, not interesting verbally. You cannot just say them to a patient, but at the same time, they trained both on these type, just output the class, like classification or you can think about it as multiple choice questions, but at the same time, they also had a prompt for actual verbal, like wordy explanation to a patient. And to be brutally honest, I haven't read through all the different results, but I guess that just from reading the abstract and the method itself, I guess that they checked, and this method probably works better than just training end to end on the verbal explanation itself. Probably also prompting the model with a special prompt to output the classes probably helped the model. I mean, the probably is the reason that they did that. So again, it's a cool trick that it's worth noting if you are into training LLMs and so on, because it is proving to be useful, and we've already seen it being used pretty successfully in a different model. So it's a pretty strong indicator that it's something worth looking into. But yeah, I think anyway, large model tricks, and it can do stuff like language models at the end of the day. But I think it's interesting to know the tricks, the small tricks that bring the models to do those stuff, because we can all just train models on data and hope for the best, but the tricks that are the things that actually push the model forward, a little bit, and sometimes a little bit is all you need just to make a model actually useful at the end. So yeah.
Yeah, I totally agree. Thank you, Tanish and Jan. So, okay, let us move on to the next paper now, which is Buffer of Thoughts, Thought-Augmented Reasoning with Large Language Models. So this is a paper released yesterday, I think. This is like a kind of like the next step, like a successor to papers like Tree of Thought and Graph of Thought. So give me a moment. Okay, so in summary, so they achieved significant performance improvements over previous state-of-the-art methods, like across many different text games and puzzles. For example, they got gains like 11% on Game of 24, which is one of the popular games for large language models, and 20% on geometric shapes and 51% on Checkmate in 1. So basically they present Buffer of Thoughts, or called BOT, versatile thought-augmented reasoning approach for enhancing accuracy, efficiency, and robustness of LLMs. So specifically, they proposed what is called meta buffer to store a series of informative high-level thoughts, meaning thought template, which was distilled from the problem-solving processes across various tasks. So here, thought template is like a cheat sheet to solve a certain type of problems. For example, a thought template may be like a step-by-step guidance on how to solve linear equations, or like quadratic equations. They basically have one cheat sheet per one type of problem. And MetaBuffer stores all these cheat sheets, and the model retrieves the most relevant one to solve the task of interest. For background, they divide various reasoning approaches into two categories: single query reasoning and multi-query reasoning. Single query reasoning basically typically focuses on prompt engineering, and the reasoning process can be finished within a single query, like chain of thought and future prompting. Multi-query reasoning basically focuses on leveraging multiple LLM queries to elicit different classical reasoning processes. So it first decomposes as complex problem into a series of simpler subproblems, like least to most prompting, tree of thought, and graph of thought. But there are a few limitations for both of these methods. For single query reasoning, they usually require prior assumption or relevant exemplars of reasoning process, which makes it impractical to manually design them task by task. So they lack universality and generalization. Multi-query reasoning is typically computationally very intensive when finding a unique intrinsic structure underlying the reasoning process for each specific task, because of the recursive explanation of reasoning path. So both single query and multi-query reasoning processes are limited by their design exemplars and reasoning structures. So they neglect to derive general and high-level guidances or thoughts from previously completed tasks. So basically, yeah, that's where prompt template comes in. So yeah, as for the method they used, they used buffer of thought to address these problems. Specifically, they designed MetaBuffer, a lightweight library housing a series of universal high-level thoughts, which is thought template, which are distilled from different problem-solving processes and can be shared across tasks. Then for each problem, they retrieve a relevant thought template and instantiate with specific reasoning structure, for efficient thought-augmented reasoning. So let me provide some example. Let's say we want a language model to solve a math problem that requires the knowledge of solving quadratic polynomial. Then it retrieves the thought template of how to solve quadratic polynomial, and the language model generates the solution by the retrieved template based in the context to use it as a guidance. So yeah, I don't know how. So I think this is a very interesting approach. I'm sure there are some limitations, like some of the problems cannot really be confined into any of a known template. In which case you have to be very creative. But otherwise, it's the performance seems very, very powerful. So I think I found it very interesting. What do you guys think?
Where did they get? I'm looking at it now, but where do they get the templates from? I mean, just like you're saying, no one guarantees that you will have a fitting template for every task. So, I mean, the whole. Okay, look, the two main ideas of first whether or not to choose explain and then solve, or solve step by step, or and so on. It's interesting. We've seen it on Orca 2 paper, but the whole taking it to a whole new level of and getting in general just I don't know a full directory of meta thoughts. I'm not sure where they get that from. It's interesting, absolutely interesting approach. I just think that the details here are crucial.
Yeah, it is a bit obscure. It is a bit difficult to figure out. So my understanding is that they sort of distilled. I tried to let the language model to distill based on the its exploration to sort of compress its path. So obviously, if they are making mistakes, then I think they are making distilling a wrong reasoning path. So I don't think that works. But generally speaking, I think you can distill like the web data into some templates, like making cheat sheets like that. So I think that may be kind of interesting. Then you can create a huge meta buffer of templates. It's a bit difficult to figure out which is interesting and which is not, because you don't want to store so many useless templates. But generally speaking, I think so this is not really explored in the paper as far as I know, but I think it'd be cool to try to generate many cheat sheets from the web data and use it.
Yeah, I'm looking now at the code. They have the distiller prompt, that is the prompt that is used to do all of this, and I mean it's a long prompt, but it's in the repo. So just anyone curious, you can go there. It's on meta buffer utils. You can see the distiller prompt. A meta distiller prompt. You are a highly professional intelligence, blah 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 blah, and a series of instructions that your task is to distill the problem. You shouldn't give the final results or possible solution in your response. And yeah, I mean, okay, it's a long prompt about how to distill problems, and I think it's interesting to reverse engineer that and maybe try to use it on different data just to see what it distills and what it gets out. But it's a really interesting approach, to be honest, to distill the cheat sheet, the method to solve problems using this, and then trying to apply this to other problems. It's a really interesting approach, I must say.
Yeah, definitely agreed. So any question? Shall we move on to the next paper?
So the next paper is image neural field diffusion models, right? So yeah, let me pin that to the space again. This is a paper from yesterday. Let me see here. Okay, so yeah, this paper is a paper from Adobe Research, like looking at high resolution image generation. So the idea is like they want, so like for the latent diffusion models, you're kind of limited by the the latents that you're training with. So it's hard to generate high resolution, and then of course with the autoencoder, that is kind of puts a limit on the sort of perceptual quality of the images. Like this is all kind of problems with the latent diffusion model that, for example, we talk about this in the HDIT paper as well. Like if you look at, example of like, generation with a latent diffusion model, and you look at like, for example, the fine grained textures and things like this, it's hard to get those, to do well, because it's basically limited by the performance of your autoencoder. So like all these different problems with latent diffusion models. So again, this paper tries to address this with a very completely different route. It's very unique, I think. It's basically that they're trying to train a model that generates neural fields. So that's it's not something I know a whole lot about, to be honest. It's more like, I think, you see it mostly used for the 3D scene generation and things like this, like NERFs and things like this, where you kind of generate some sort of neural representation of a scene, for example. But I guess you can also do the same for images. Here we can generate a neural representation of an image, and then you can render that image. But the idea is you can generate this representation of this image, but now it's not limited by the resolution, so you can then render it at any resolution that you want. And so, for example, you can then render it at a high resolution. And so then the idea that they have here is that they what they do is they have to first train autoencoder, or I guess it's not really an autoencoder, but basically it takes in images and generates some sort of latent from that images, and then you have a decoder, which is this, I guess, neural renderer or whatever they want to call it. I guess they call it a neural renderer, where it generates that sort of image. It generates that neural field from the latent, and then you can render from that image field the final high resolution image, for example. So they have to train the encoder and the decoder first in order to be able to do this. And so they have specific sort of laws for training this sort of neural field generator, this sort of neural field renderer, that decoder part, and so they have to first train this on a whole bunch of images, and they use a GAN loss for that as well. They have a GAN loss in there, again, to improve perception quality and things like this. And then after you train that, then you can train a regular latent diffusion model on the latents from this autoencoder. And so then you can just train a regular latent diffusion model, and that gives you high resolution image generation. And also, the good thing is because you can also train on varying resolutions. You don't always have to train on just high resolution images. You can train on different resolutions all at once. And also, you can utilize limited number of high resolution images. So they have various experiments of that, where you train with different levels of high resolution images, or different number of high resolution images, and show that they can get performance.
I hear some noise.
Oh, okay. Let me make sure.
Oh, okay. Hey, you know what?
Let me talk. Yeah, let me just talk a little bit louder. Is it better now?
Not much, to be honest. I mean,
it's not better.
Slightly, I guess. Well, it's so
Okay. Okay. I was trying to talk louder, and it should hopefully also should get better. But yeah. Yeah. So I was just saying, like, with the what was I talking about? Yeah, like you can train on different resolutions, and also you don't need as many high resolution images for this method. But yeah, I think their comparisons weren't very comprehensive. So it is a little bit limited, and I think they didn't compare to a lot of other methods per se. So I'm not particularly sure. I mean, for example, they didn't compare to. I don't think they compared to HDID, if I recall. So, like, for example, yeah, I'm just. This is a very unique approach, though. Like this whole idea of like generating a neural field and then using that to give high resolution images. It's like a completely different approach altogether than a lot of other approaches are trying to either just improve the latent diffusion model directly, or like we did with trying to do direct pixel space generation, all these other approaches. So this is a completely unique approach. So I think that was kind of interesting. But I think the comparisons may be a little bit limiting, and ideally we'd see more comprehensive comparisons. But yeah, apart from that, I think it's a great paper, and I mean the Adobe research team overall publishes lots of interesting research in the image generation space. So yeah. Any questions?
Oh yeah, I totally agree. I really like this report. Thanks for letting me know of this paper. Generally speaking, I really hate resolution fixed approaches. Like a resolution, it should be agnostic, and so yeah. Hopefully, this model, this approach is going to work on many different cases. Yeah, I want to see more evaluation and future models on it. Yeah, it's not really a question. Anyone else has any question? Okay. Tanish, do we wanna move on to the next paper, or are you getting any? Okay, I can move on to the next question. Sorry, next paper. So actually, the next paper is not really a paper. It's more about like a set of papers. The thing is, there are so many papers sort of related to synthetic data augmentation.
Sorry, I lost connection for a bit. Yeah, you can continue on. I don't know if you're waiting for me or anything.
Yeah. So I will present some interesting results from some of the recent papers about synthetic data augmentation and at my observations. So state-of-the-art large language models use datasets with tens of trillions of words and use from 2 to 3 times more data per year. So Epoch AI's recent paper estimates when we might exhaust all text data on the internet. And apparently it's not too far away. So there's at least one way to avoid this problem. I'm sure there are more than one way, but this one's the one I know. And continue training on more tokens, which is to leverage LLMs to perform data augmentation on the existing data. So there are many ways to perform LLM-powered data augmentation. The most straightforward approach is to rephrase a sample in many different ways. One can also completely change the format of the sample, for example, by converting a Wikipedia article into dialogue format. One can also translate or summarize the sample, or even generate many question-answer pairs about the sample. One interesting fact is that language model trained on a synthetically data augmented dataset, where they are, for example, 10 different samples generated from a given sample, it does not overfit like when you train a language model for 10 epochs. So I think that's kind of interesting. Generally speaking, as long as the augmented data are different enough from each other, overfitting does not seem to occur. So in here, what I meant is that training loss is not gonna just keep going down, and test loss is gonna going up. So that kind of thing does not occur. Overfitting may have more to do with exact copies than contents having the identical information. So here's a relevant example. So there are many news agencies that publish news articles, but most news were bought from AP, AFP, or Reuters. So people are essentially augmenting the same sample using a small amount of extra information. But training on synthetically augmented dataset may potentially slow down the training because this process does lead to reduced data diversity. It is not well known how much slowdown this results in, but it'll be interesting to investigate this. So the thing is, large language models and many other neural networks have very poor sample efficiency compared with, say, humans. This has been known for a while, but recent papers like no zero shot without exponential data have thoroughly shown that a model needs to be trained on many different instances about the same entity before being able to actually learn about the entity. For example, this means that fine-tuning some pre-trained model on a single news article from today, it does not make the model understand the article at all. You need at least a dozen distinct news articles from today that cover the same exact same event to make it work. Obviously, in-context learning resolves this problem because in-context learning is sample efficient, but this shows that gradient descent is very sample inefficient and cannot really carry over the information to the next iteration. But synthetic data augmentation mitigates this problem. According to some of the recent papers, there have been several papers that fine-tune a language model on synthetically generated question-answer pairs produced from the latest articles that are unseen to the model, and observed some notable performance improvement. So or you can even consider gradient descent as sort of like a recurrent neural network. So RNN sends signals to the future via memory vectors. We can view gradient descent as RNN for sending updated parameters to the next iteration. Unlike common RNNs like Mamba, the size of its memory vectors is massive for being equal to the number of its parameters. It can technically send signals to the hundreds of billions of tokens, signals to the future of like hundreds of billions of tokens ahead. So I think that'll be kind of interesting. I didn't really see this kind of thing being talked about, so I'm guessing that synthetic data augmentation is going to be very, very important for many different reasons. And reinforcement learning its performance is often boosted by data augmentation. So I think this also is going to help a lot. So yeah, I guess that's about it. Do you guys have any comments, questions?
I think we can also explain this by interpolation. For example, you have instruct data and you have your just raw news article, for example, and you want to ask question about the news article. So it is much easier to interpolate to a news article in an instruct form if you already have the news article with some questions below it. So I think we can explain this by easier to interpolate to answering about the news article if you have this augmentation. But yeah, I think also that I don't know. I really like the analogy of RNN sending gradient descent being RNN. I never heard this before, and it's a really interesting thing to think about. Sending information into the future as through the parameters, which is a really cool thing to think about. But yeah, I mean,
yes.
I mean, obviously, look, if you train a single time on a news article, I think we'll understand that the model just not going to just memorize it, obviously. So yeah, I think this approach is promising at the end.
Yeah. So training a model about like a question answer pairs generated about that article sounds kind of cheating because it's exactly about the same thing, and the model can answer those questions because it was trained on it. But generally speaking, compressing samples in certain article samples into the model to make it actually understand that particular example is not a trivial question. So we may have to do something like this. As for RNN analogy, so if you have some recent RNN papers like Mamba2 or the latest RWKB paper, you can see that those papers have achieved huge performance boost or like a long context performance boost, but because they increased the capacity of the size of memory vectors. So they used to bring only like a single vector into the future or something like that. But now their memory vector size is much bigger. So they have more capacity, so they can send more information to the future. And if you think about it, their memory vector size is far smaller than their parameter size. So if we can compress information into the entire parameter, then it should make it we can send the information to much farther future. And so that's basically the reasoning. So yeah, I don't know if this is gonna be effective or not. I'm trying to figure out. Yeah, also hopefully we're gonna see some papers like this more and more. That's exciting yet sort of overlooked direction, I guess.
The whole thing became meta on meta on meta. You have the parameters, the gradient descent is sending through the parameters signal into the future, and the parameters themselves represent a neural network that can be an RNN on the context. And you have in-context learning. At the same time, the model is also learning through the fine-tuning into the parameters themselves. And the whole thing just became one giant meta of meta learning. The model learns to be a meta learner or at some sort through the context and through the parameters and through the training itself now. And it's really cool if you think about it, how far we've come with this whole approach of general models. It's really cool.
Yeah, I totally agree. At the same time, we are sort of revisiting all the concepts, and that's also cool too. So yeah, Tanish, do you have anything to add or?
Yeah, I remember I don't know if you remember this. There was a paper maybe a month or two ago that analyzed this. Yeah, the use of synthetic data, and they were saying if you train, I think they looked at some toy examples just to kind of better study this, and they were saying if you train on just synthetic data, then you have this case of degeneration where the model will it will kind of fail to learn. But then if you mix it with the real data, then you consistently will get improvements. This was a paper maybe about a month ago or 2 months ago. I think it was about a month ago. I don't know if anyone remembers this paper.
That's a rephrasing paper, right?
It was not rephrasing. It was about just generating. It was a very simple test or a toy example kind of they weren't looking at, I don't think they were really looking at real world, but they were kind of just trying to analyze this case of like degeneration with training on synthetic data. And they were saying like, yeah, if you train with a mixture of synthetic and real data, then you won't get any problems. But now I can't remember what that paper was called. Yeah, I mean, I think you also mentioned the same.
Oh, sorry, you're cut off. Oh, I cannot hear you yet. Oh, well, okay. Yam, do you have anything to add?
No. I think I said what I think about this paper.
Sounds great. Okay. Then, yeah, I really hope Tanis to get back, but yeah, it sounds like his connection is bad. So maybe we can end the session now. Yeah, thank you so much for coming.
Sorry, I'm back. Did you? Hello?
Oh, yeah, go ahead. Tanis, were you trying to say something?
Oh yeah, I was just saying I can't figure out what that paper was, and if anyone remembers what that paper was, yeah, let me know. But yeah, that's all I had. Sorry, I think I just lost the connection for a second there, but yeah.
No problem. Yeah. So thank you for coming.
Is there anything? I mean, if there's anyone else want to talk about bring up anything, or if did anyone have any last minute questions? I guess maybe one thing to briefly mention in terms of like AI news, of course, is that like, the Stable Diffusion 3 weights, the Stable Diffusion 3 medium weights were released. So that's the 2 billion parameter model. Those weights are up on Hugging Face now. And then I guess I saw like Llama Labs has released some sort of video generation model that people can try out, I guess, for free. It looks like I haven't played around with it yet, so I don't know. But it looks like that's been released too, or to try out. So yeah, I think there seems to be some interesting AI news today. But yeah, anything else worth pointing out? I guess before we end.
Not on top of my head. Those sound very exciting.
Yeah, cool. Anything else you want to add?
No, not that I can think of.
Cool. Yeah. Sorry about all like the noise and stuff. I was traveling a little bit, so sorry about that. Yeah, thank you everyone for joining. Yeah, thanks all, and I guess we will talk to you guys next week. Thank you everyone for joining.
Thank you. Next week. See you next week.